the functions, okay, polynomial functions. We don't want to have to investigate, let's say, like x squared, learn everything we can learn about x squared, and then learn something about x cubed, learn everything we can about x cubed, then go to x to the fourth, and do that for every one as the exponent increases. So I don't want to learn something about x. I don't want to learn x squared all by itself. I don't want to learn x cubed all by itself, x to the fourth, x to the fifth. Because when I do that, then that means I have to learn x to the 31st all by itself. And I have to learn x to the 454th all by itself. And if you think about that, that's going to be an infinite number of polynomial power functions that I have to deal with and understand individually. And I can't do that. Learning an infinite number of things is impossible, right? Okay. But if we can group them and learn them relationship-wise, basically what happens is we learn two groups. We learn even power degrees and the relationships that exist there. We learn odd power degrees and the relationships that exist there. And if we can do that, instead of learning an infinite number of things, we learn two things. Okay? Along with them, the relationships and the behaviors that those things share. So here's the idea. It says the graphs of polynomial functions and behavior. The first thing we'll talk about before we get back into what we were dealing with yesterday is what we call continuity. Okay? And deciding whether a function is continuous or not. Okay? This becomes one of the most important properties that we deal with inside calculus. Okay? There will be theorems, there will be rules, and stuff like that you apply for only functions that are continuous. Okay, so the theorem will say if f is continuous on some interval I, then this is what you can do. Okay, so the first thing you have to do is determine, well, okay, is the function I'm interested in, the function I'm working with, continuous on this interval that they're talking about. Okay, if I look at this picture right here, so when I say that interval I, right now, maybe I'm just talking about all real numbers here. Okay. In calculus, and I'm not going to spend a whole lot of time on this right now, but in calculus, the idea about continuity is founded in what we call limits. Okay? Let's say, let's call this value A. Okay? What a limit is, and people think it's harder than what it is. It's actually a really easy concept. A limit is just asking you, what is your y value getting close to? Okay? Not asking what your y value is. So I'm not going to ask you what the y value at A is. I'm going to ask you, as they get close to A, what is your y value getting close to? Does that make sense? Okay? It's the idea of approaching a value. Okay? Not actually getting to a value. And this limit is actually the foundation then of calculus. Okay, it allows a lot of the calculus that we do to exist. But the idea says as x moves along the horizontal here, and it gets closer and closer to this a value, closer and closer to that. Maybe that a value is 3 or 4 or whatever. Okay, but as x gets closer and closer to it, moving from the left, you kind of think about what is your y value doing. Okay. Well, when it's over here, my y value is there. When x is here, my y value is there, so it's increasing a little bit. But as I get closer and closer to A, wouldn't you agree that as I get closer and closer to A, my y value is getting closer and closer to y1? Does that make sense? Okay. So what we would say here in calculus, you don't need to write this down, is that the limit as x approaches A, and we put a little minus sign up there as a superscript, and that just means from the left. We would say that limit is, so let's call this function f, okay? We would say that limit is equal to y1. As I'm moving from the left to this a of this function, I'm getting to a y value of y1. Let's look at this as we move from the right. As I move from the right, closer and closer to that a value. So the way we would write that is the limit as x approaches a. But now I'm moving from the right, so what do you think superscript-wise I would put here? Plus sign. Okay. Of this function f. As I'm moving to A from the right. Now I would be on this part of the graph, right? Okay, so these would be my y values. What's my y value getting closer and closer to? Y2. Okay, the idea is if those two numbers are the same all the time on the graph, meaning no matter what A value I use, I get to the same y, then we have what we call continuity. If they're different, and that's what we're seeing right here, they're different, that means we are discontinuous. Does that make sense? Okay, it means there's two different y values that I'm approaching here from the left and from the right. If my A value was here, let's say my A value was right there, would you agree that from the left, as x approaches from the left, that you would be approaching y1? Make sense? Yeah. From the right, would you be approaching a y value of y1? Okay, so in that situation, if that's the A, then we would have a y1 here, and we would have a y1 there, right? See how they're the same? If a function is continuous, that will be the case for every single A value that we choose on the x-axis. If we ever get them to be different at some particular A value, then we break our continuity rule. Okay? So that's the calculus. And that will make more sense, guys, when you investigate. So you'll deal with limits for probably, it depends on when you take it. As a high school student, you'll probably deal with limits for, I don't know, 3, 4, 5 weeks. Taking college, you might deal with limits maybe 2 class sessions. Okay, but that's the idea. Okay, in layman's terms, okay, so in like maybe non-mathematical terms, the idea is if the limits are the same at all x values, okay, the limits from the left-hand side are equal to the limits from the right-hand side for all your x values in the entire interval you're looking at, the function will be continuous. If they're different anywhere, it's discontinuous. But the idea says if it is the same through all these x values, basically means you can graph this thing, you can put your finger on it, and you should be able to trace this whole graph without lifting your finger. Okay? Well, if my cursor is my finger, don't I have to lift my finger to get up here, continue to graph it? Same thing there at that hole, I have to lift and continue to graph it. Does that make sense, everybody? So because I had to lift my finger here and lift my finger there, that tells me that limit issue was existing. Okay, I've got problems with that limit. So this thing would be what we call discontinuous. It is not continuous. Okay, a graph like, let's say, a graph like that. Can I graph this whole curve without lifting my finger? Trace the whole thing without lifting my finger? That thing would be continuous. Okay. If I had something maybe like this, so something like that. Okay. That's a hole, right? Okay. It means we do not have an x value. Now, this is a function. But if I were to trace this with my finger, that's a hole. Okay, so I can't just trace right through it. Does that make sense? I have to lift my finger over top of that. That means this is not continuous. Okay, if that hole was filled in, I can trace that thing without lifting my finger, and it would be continuous. Okay, does that make sense, everybody? I'll give you on your next quiz. We're gonna give you a series of like 6 of these. Graph is basically all you gotta do is go to the furthest left part of the graph, put your finger on it, and see if you can trace the whole thing without lifting your finger. If you have to lift the finger, automatically say discontinuous. Okay. We have a quiz tomorrow. Should always be prepared. These are some relationships that exist with all polynomial functions. Okay. We've got 3 graphs here, 2 of which are polynomial functions, 1 is not. Okay. Which ones look similar up there? Which 2 graphs look? Second, third, right? Okay, so the second, third look very similar. They're smooth, okay, and they're continuous, right? Smoothness, and continuity are two features of all polynomial functions. Smoothness and continuity are features of all polynomial functions. Okay? So any x to the n, a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, that whole garbage thing that we talked about earlier in the week, anything of that form is going to produce something like these two. It will never produce something like this. Okay? We've got some weird things going on algebraically when we get something like that. We call that a corner. This here is called a cusp. Okay? When you have those things, those are graphical indications that the rule that they came from, the f of x that they came from, was not polynomial. Does that make sense?
Can you write this down?
Okay, I would. Okay, now what I would write in mind, I want to draw all those pictures, but I would write that all polynomial functions are smooth and continuous. Okay, there are no corners, there are no cuts, there are no sharp edges or anything like that. Okay, because again, I might give you in a quiz, might give you 3 or 4 of these, and ask you based on what we've talked about here. Identify which ones are likely to be polynomial functions and which ones are likely not polynomial functions. No.
You should know. Did you answer Tyson? You don't have to look at it until you make it. Be sick.
Oh, fuck no.
Go ahead.
Yeah.
No, it's for a favorite club.
That's not sleep the whole time. This is the first time I've seen everyone awake. I just don't sound pretty kind of right.
All right, so we talked a little bit yesterday about end behavior. Okay, what end behavior is the idea. If I've got my x and y axes here, okay, every graph, and this is just right now talking about polynomial functions. All functions have some type of end behavior. Okay, but polynomial functions are going to be right now a unique set of functions. And the idea is as x moves to infinity, your y values have 2 options. Your y values, so as x goes this way, your y values could go up. Or maybe as x goes this way, your y values could go down. Does that make sense? So you got 2 options. As x goes to infinity, your y could go to infinity, or your y could go to negative infinity. And the same thing happens this way. As x, I'll write this kind of backwards, as x goes to negative infinity, x goes to negative infinity, your y values could go to positive infinity, or your y values could go to negative infinity. Does that make sense? Okay. And we should be able to develop an understanding of what is happening just based off of what the function rule looks like. And all of this, and we'll spend a lot more time tomorrow algebraically talking about why this is true, but all of this is dictated by the leading term that Don talked about as the dominating term yesterday. Okay? So if I have a polynomial that has 25 terms in it, so maybe I got a degree 25. So I got an x to the 24th, an x to the 23rd, x to the 22nd, all the way down to x to the 0. The only term that dictates the end behavior is the x to the 25th. The other 24 don't matter at all. Okay? And we'll kind of examine why that's true tomorrow. But end behavior, we talked about for odd degree polynomials yesterday. So I've got this set up from last class. We'll just use this one. This is x to the first power. Okay? And my hope is that we can see, and I made these blue for a reason. So the blue part of the graph is representing what the graph is doing in the long run, right? And as I go out in the x direction, out to a very large x value, what is the y doing? Okay, well, out at 60, the y is up at 60, right? Yeah. So when I go out to x to be 100 million, y is going to be at 100 million, right? So the x goes out to infinity, y is going to infinity, right? If you understand that in behavior right there, as x goes this way, as x goes to positive infinity, y also goes to positive infinity, every odd degree polynomial is going to have the same behavior. So when I go x to the third, as x goes to positive infinity on the x-axis, so I go to 2, to 3, to 4, all the way down to 100 million or 100 billion or 100 trillion, okay, or septillion or whatever. I go out to a googolplex, okay, then the y value is also going to go to a very, 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 very large number, right? So as x goes to infinity, y goes to infinity. Okay? That make sense? As x goes to negative infinity, where's y going? Negative infinity. Is that true as I go x to the fifth? Is it true for x to the seventh? Okay, so here's the idea. Y learns something about x to the third in isolation, and then learn something about x to the fifth in isolation, and then learn something about x to the seventh in isolation. Because once we do that, if we learn them all in isolation by themselves, aren't you relearning the exact same thing over and over again? Okay, it's redundant. So, as we work with, right now my A value, right here from x to the left, my A value is positive. It's positive 1. That's the only thing I've got graphed here. So these sliders don't matter for the graph we got highlighted. So my A value is positive 1. If my A value, let's put an A out here. As A, so we're looking right here. That's the function that I want you guys looking at. That's the rule. As my A goes through positive numbers, does the end behavior change at all? No. That A just makes those y values go larger faster, right? Okay. So I'll hit a value of, on this one when A is just 1, I don't get to 8 until I get up to an x value of 2, right? But here, I'm going to get to that value of 8 much quicker than 2. Okay? So that's kind of the idea of what that A value is doing. Now, when A is negative, what's a negative out in front of any polynomial going to do? Reflect it. Okay? So now, if I reflect over the x-axis, does it change the end behavior? Yeah. Okay? Now the end behavior as x is going this way, your y is going to negative infinity, right? As x is going to negative infinity, your y is going to positive infinity. Okay? That's true for all A values that are negative. As I move this thing through A values that are negative, it doesn't really change what's happening in the end behavior. Now the red stuff is changing, right? The stuff, the behavior of the y values near 0, 0, that kind of stuff are changing. We'll talk about that later on. But in the long run, as x gets very, very large, the only thing that's changing is the stuff that's close to 0, 0. The end behavior stays the same. So here's the idea, and I don't like the way they write this. It's kind of, I think it's backwards. I would write this. So I would draw these pictures.
Well, let's draw you.
Huh.
All right.
So I'd be writing here, so this is A is greater than 0, so A is positive. And I would say as x goes to infinity, where's y going?
Infinity.
Y is going to infinity. As x is going to negative infinity, y is going to
negative infinity. This one here, a has got to be what? Less than 0. A is negative here. Okay, so my coefficient of my polynomial, my leading term is negative. So here as x is going to infinity, where's y going? Negative infinity. Here as x is going to negative infinity, y is going to infinity. And that's based off then, guys, every polynomial that is of that form. Okay, now the idea then, okay, so that's our polynomial of that form. The only thing that's dictating that in behavior is that term right there. Everything else, all these other terms in our polynomial are garbage and mean nothing in regards to end behavior. Now, the idea yesterday we said, okay, if I have x to the fourth and I plug in 100, okay, then I have a 1 and then 8 zeros on it, right? Okay, which is what? What's that? 100 million. Okay, that ends up being such a much more dominating value for my y than the x to the third. Okay, when I plug in 100, it only gives me a million. Okay, so we'll talk about that. You know, a million's a lot, right? Yeah. But 100 million is exponentially larger. It's a lot more. Okay, and so that's a dominating amount that impacts the y much more. So that's the only. We'll talk about that algebraically tomorrow. Hopefully, it'll prove a point to you tomorrow. The thing I want to talk about here is these dots. Okay, we don't have enough algebra sense yet, and it doesn't come until calculus to really understand precisely what those things are doing. We will learn a rough sketch of what's going on with these dots. Okay, how many maximums and minimums we have. You know, how many y-intercepts, x-intercepts, all that kind of stuff from our function. But to really get a good understanding of this dotted stuff, we need what we call the first derivative test and the second derivative test in calculus. Okay? Or at least those things will do it a lot faster for us than our schools. But what I want to show you here is if I graph, this is an x to the, I want to make this x to the 7th. Okay? But here is my polynomial, x to the 7th, negative 2x, or 2.7, x to the 7th. Okay, now, I wrote it, and GeoGebra won't, so this is to the 6th, right? Does that make sense? This is to the 5th, this is the 4th, 3rd, and then squared, right? Okay? It just, because I wanted it based off of this n, so when that n changes to 9, I want this to be 8. So I had to write it in using variables, and it just won't clean up. But this is, let's make the a value positive. Okay, so let's make just the a value 1. That's x to the 7th, right? Now, it's all these other things are kind of ugly, but is that the same end behavior that x to the 3rd has? Okay. Now, I'm going to mess around with the b value, the c value. See if we can get this thing to do some weird things here. You can kind of see see if I can get some. I used to. All right, so there's some weird things going on here, right? Okay, this behavior, let's say, let's go if, let's go between negative 0.3 is less than x is less than 1. That's a go 6. Let's ask this thing to graph p of x, and we'll put that, hopefully that'll make it a different color. Okay, so you kind of see that purple stuff, right? Yeah. Okay, that's some weird stuff going on there in the purple that is different than what happens with x to the 3rd. That's different than what happens with x to the 5th. That's different than what happens with x to the 9th. Does that make sense? Yeah. But everything that stayed red, the end behavior is identical for x to the 7th, as x to the 5th, as x to the 3rd, as x to the 9th, as x to the 91st. Okay? And that's kind of what we're going to try to investigate and understand. Okay? What things are creating relationships or creating a behavior in the long run as x is
really, really big in both directions, positive and negative. And then tomorrow and the next day, we'll investigate, okay, how do I know what's going on with that person? Based on that X to the 7th, how do I know that I've got 1, 2, 3, 4 potential turning points up there, 4 basic max and minimum in that purple range? Does that make sense? Okay. So there are some things by this rule up here, by looking at this polynomial form, by looking at that number and understanding the end behavior, there's only so many other things that graph can do in regards to like maximums and minimums. Does that make sense? Okay. Think about this. If it's x to the 7th, if it's x to the 7th, and I'm thinking about end behavior, x to the 7th, I know end behavior has to be that way, right?
Yeah.
Okay. If it's the 7th power, let's think about this. If I have one maximum, okay, doesn't that mean I'm going to have a minimum so I can get back up to this end behavior?
Right.
Okay, so let's say I have that. Okay, so my x to the 7th could kind of look like that. Does it make sense?
Yeah.
But could I also maybe do this?
Yeah.
Okay, so then to be an x to the 7th, doesn't have to turn again to get back up there? Okay, so that's 1, 2, 3, 4 turning points, right? Okay, we could actually have a 5th and then a 6th. Okay, now we'll talk about this tomorrow. We can't have 7 turning points. The 7 turning points will give me an end behavior where it'd be pointing down to the bottom right. Okay, I can't have 8 turning points. Because I have 8 turning points, and that says something about how many zeros I could potentially have, which would mean that I have more than 7 zeros, which is more than the exponent of the polynomial I started with. So what we're going to find out tomorrow is if I have a 7th degree polynomial, I can only have, at most, 6 turning points, or 6 maximums and minimums. So somebody else tomorrow, we'll start with tomorrow. No new homework.
Friday, no good tomorrow? Yeah, actually,
Friday.
Friday.
Wait, what do we have next year? Third period?
Come on, Chuck.